Hello, this is the lecture number 2 on the theory of games and vaccination. So we continue discussing the material that you can find in this reference. This is an article by Ern and Bach, Vaccination and the Theory of Games, published in 2004. So what we will derive in the next few minutes is an expression for a probability of infection, as this probability of infection can be considered a function of a specific level of vaccination coverage or the vaccine uptake in the population. So we again make reference to the basic epidemic model without dimensions, the dimensionless SIR model, and we're gonna pay particular attention to the compartment for susceptibles. This compartment has some gains and losses, and we're gonna call the losses or the things that are being subtracted here departures from this compartment. And we know that the departures from this compartment due to infections are in the new parametrization of this model are in terms of R0 and 1 plus F. So this expression, you can see how this expression is being subtracted from the susceptible equation, appears as a loss for the susceptible compartment, and it also happens to be that same amount is a gain for the compartment of infectives. On the other hand, we have that for the susceptible compartment, the total losses are given by that term, the new infections or the context between susceptibles and infective, together with what will be considered now like the departure due to, in analogous to what would be the death rate for the S compartment. So if we wanted to count the total departures, then we would consider this quantity here is the total. We consider that as the total departures from the S compartment. Next, we'd like to define the probability of infection, specifically the probability that an individual will eventually become infected for a specific level of vaccination coverage in the population. In other words, if the vaccine coverage level in the population is P, then we write this symbol pi resembling probability sub P, where there is a dependence of that probability on the level of vaccine coverage in the population. And to do that, we're going to combine the previous expressions, the expressions we just discussed. Okay, so we're going to define this probability of infection at the vaccination level P to be the departures due to infections from the susceptible compartment out of the total number of departures. And you may want to note that this expression is written here in terms of equilibrium quantities. That is, S is evaluated at its value at equilibrium, and I is evaluated at its value at equilibrium. And what we give particular emphasis here is to the values at the endemic equilibrium. In fact, these values we could write an expression here. So we would have that S bar, this is something we had previously discussed, S bar is given by 1 minus P sub C, where this is the level, the critical level of vaccine coverage, and then what we mean here by I bar is an expression that reads as F over 1 plus F multiplying P sub C minus P. Okay, and this is all in a context in which p sub c minus p is positive, right? We're assuming that um, the endemic equilibrium is we have the two assumptions here for the endemic equilibrium to be stable. So it turns out that we can actually work some algebra here, and we can simplify the expression for this probability of infection. In particular, we want to consider the first equation set equal to 0. Okay, uh, we may want to recall that when we compute the quantities S bar and I bar, the equilibrium quantities, we're really dealing with um, equilibrium equations, right? Both derivatives are set to 0, and one would solve for S and I, and those are the expressions. Those are how we obtain expressions for S bar and I bar. So by doing so, by setting that, considering that equation, we find that it's possible to obtain an expression equivalent for the total number of departures. So we can um, rewrite, in fact, this gives us an expression for both the numerator and the denominator of this expression, right? So let me go back here. So we have an expression, it's clear that we have an expression for the total number of departures, which is this. However, from this equation, we can move this expression f minus s bar to the right-hand side, right? We can have here that minus f times s bar plus f times 1 minus f. We can have that equals r0 times 1 plus f s I. This would be s bar I bar. Okay, so we have also an expression for the numerator in that expression for pi sub p. So we using those substitutions, then now pi sub p takes this form. Okay, it's easy to see here that we can um, cancel the f that appears in every expression, numerator and denominator here. And what we will do next is find an expression for S bar. So we know that S bar is written as, let me see if I can go back here. So we know that S bar is written as 1 minus P sub C, and using the definition of P critical, we find that S bar, this is 1 minus this part here is what we have an expression for P sub C, P critical, and then we find that S bar equals the multiplicative inverse of R naught. So S bar equals 1 over R naught. This means that we could go back and make a substitution in this expression. So pi sub p, by substituting this S bar with 1 minus R naught, 1 over R naught, then this now takes this form, and we can do a further simplification here and find. So we do an extra step then, and we have a much cleaner expression for this probability. So in fact, that probability is 1 minus 1 over, this denominator is R0 times quantity 1 minus P. Okay, so and this is what we have done. We have derived this probability at a particular level of vaccination coverage. Notice it's important to note that The only parameters involved for this probability are the basic reproductive number and P, the vaccine uptake in the population. So in this way, we have derived an expression for pi sub p, pi evaluated at p. This expression, there is much more to do, much more remains to be done with pi sub p, but we recall or reflect right now that this will be an important model parameter, if you will. This is the probability of an individual that is not vaccinated, an unprotected or unvaccinated individual, the probability that such individual becomes infected given a specific level of vaccine coverage in the population, pi sub p. And stay tuned, and we will continue doing much more mathematics in this context of vaccination game theory, making specific use of pi sub p.